Hey everyone, in this video we're going to go over section 4.4, indeterminate forms and L'Hopital's rule. So up until this point we actually don't have the ability to solve limits like this. The limit as x goes off to 1 of the natural log of x divided by x minus 1. The issue we run into is that the numerator goes to 0 and the denominator also goes to 0. When we get something of the form 0 divided by 0, we label or we denote limits like this as being an indeterminate form, meaning that we can't really determine the value of this limit in its current form. Typically when denominators go to 0, limits go to either positive or negative infinity, and when numerators go to 0, limits go to 0. But because we have this 0 divided by 0, we can't get something concise out of it in the form that it's currently written. Similarly, if we wanted to take this limit to infinity, as x goes out to positive infinity, because the natural log is only defined for positive real numbers, natural log of x divided by x minus 1, and this goes off to infinity divided by infinity. Once again, we don't get any good information about infinity divided by infinity. We don't know, is one larger than the other? Does this settle down to a certain value? Remember, limits going to either positive or negative infinity is asking about horizontal asymptotes. And L'Hopital's rule gives us the ability to deal with limits that kind of return a value of either 0 divided by 0. So this is L'Hopital's rule. We'll write it down. And what L'Hopital's rule says is, suppose an f and g are differentiable. Suppose functions f of x and g of x are differentiable and g prime of x is not 0 on an open interval I that contains a. So on an open interval, we're going to call that interval I, and somewhere in that interval that contains a. So somewhere in this open interval around a, except possibly at a itself, so, and then suppose that, we've got two things. Either the limit as x approaches a of f of x equals 0, and the limit as x approaches a of g of x is equal to 0, or the limit as x approaches a of f of x is equal to plus and minus infinity, and the limit as x approaches a of g of x is equal to plus or minus infinity. Then the limit as x approaches a of f of x divided by g of x is equal to the limit as x approaches a of f prime of x divided by g prime of x. Then the limit, let's see, if the limit on the right side exists or is positive or negative infinity. Perfect. I kind of ran out of space, but the whole idea of L'Hopital's rule is that, so we have a quotient of functions. Let me grab another piece of paper. We'll take this limit. The limit as x approaches 1 of the natural log of x divided by x minus 1. And remember, limits are easiest when you can just take this number and plug it into our function. So that's the first thing we do. If we do that though, the natural log of 1 is 0 and x take away 1 is 0. When we have this 0 divided by 0, this sets us up to use L'Hopital's rule. I'm going to put a LH so you really tell the reader where this next step comes from. By L'Hopital's rule, the limit as x approaches 1 of the natural log of x over x minus 1 is equal to the limit as x approaches 1 of the derivative of the numerator is 1 over x, and the derivative of the denominator is just 1. Well, we can still algebraically manipulate this thing. This is equal to the limit as x approaches 1 of 1 divided by x divided by 1 is just 1 over x, which is equal to 1. So, L'Hopital's rule allows us to take the derivative of the numerator and the derivative of the denominator. That's one thing I want to write down. We are not using the quotient rule. We're not using the quotient rule. What we're doing is we're taking two functions, f of x divided by g of x, and we are just taking the derivative of the numerator and the derivative of the denominator. No quotient rule, just straight derivative numerator and straight derivative denominator. So L'Hopital's rule is actually pretty powerful. Before we had to use a geometric example, or we had to prove geometrically that the limit as x goes off to 0 of the sine of x divided by x is equal to 1. But aside from using a graph, what we know by L'Hopital's rule, when we try and plug 0 into this equation, or in here, we get a 0 divided by 0. This will go to 0 divided by 0. So what we know is that the limit as x goes to 0 of the sine of x divided by x is equal to, by L'Hopital's rule, the limit as x goes off to 0 of the derivative of sine is cosine, and the derivative of x is 1. Well, the limit as x goes to 0 of cosine of x is equal to 1, and the limit as x goes to 0 of 1 is 1, which gives us 1. So now we no longer need to use a geometric proof to get this result. We can just apply L'Hopital's rule. Once again, this step, it's not always immediately obvious to the reader. You guys are still learning, you guys are still developing the skills for taking derivatives. So what if you make a mistake going from here to here? Without telling me that you used a derivative to go from this step to this step, my mind automatically goes, okay, what algebra did they use to go from this step to this step? So when you're doing these, please, please, please show me that you used L'Hopital's rule. I don't care if you put a LH, that's what my teacher told me to do when I was in Calc 1. Denote to the reader, and I'm your reader, that you're using L'Hopital's rule to go from this step to this step. So, not immediately obvious from the statement of L'Hopital's rule, and I don't know why the book didn't include it as a footnote, but we can also, instead of going strictly to A, we can take one-sided limits as we go out to infinity. Like over here, a one-sided limit as we go out to positive infinity, or a one-sided limit as we go off to negative infinity. So, by that, I mean if we wanted to calculate what the limit as x goes off to positive infinity of e to the x divided by x squared. So we always want to try and just substitute in and see what we get. Well, if we try and see what happens as x goes off to positive infinity, well, the numerator goes to infinity and the denominator goes to infinity. Fine, this sets us up to use L'Hopital's rule. So we know that the limit as x goes off to infinity of e to the x over x squared is equal to, by L'Hopital's rule, the limit as x goes off to positive infinity of derivative of e to the x is e to the x divided by the derivative of x squared is 2x. And now if we want to try and apply this limit, what happens as x gets big? Well, our numerator goes to positive infinity and our denominator still goes to positive infinity, which is fine. We can just apply L'Hopital's rule again. So this is equal to, by L'Hopital's rule, the limit as x goes off to infinity, derivative of e to the x is e to the x, divided by the derivative of 2x is just 2. Now what we get as x goes off to infinity is we get infinity divided by 2, which is just infinity. So we have shown that this function does not have a horizontal asymptote. Remember, limits going to positive infinity or negative infinity is another way of asking about horizontal asymptotes for this function. So what this is saying is this function grows without bound as x gets really large. So moving on, let's do some more. We're going to calculate, this is example 3. What we want to do is we want to calculate the limit as x goes off to infinity of the natural log of x divided by the square root of x. So the first thing to know is, well, what happens if we try and just directly solve this limit? Well, this thing is going to tend to, the numerator tends off to positive infinity and the denominator tends off to positive infinity. Wonderful. We now have the ability to just not throw our hands in the air and say, I don't know. We can apply L'Hopital's rule. So we know that the limit as x goes off to positive infinity of the natural log of x divided by, and I'm going to go through and I'm going to rewrite the square root of x as x to the 1/2 is equal to, by L'Hopital's rule, the limit as x goes off to infinity of derivative of natural log of x is 1 over x divided by the derivative of x to the 1/2 is 1/2 of an x to the negative 1/2. Now what we want to do is we want to go through and we want to algebraically manipulate this thing. So let's multiply top and bottom of this equation by x over x. So when we do that, this is going to be equal to, not by L'Hopital's rule, but by algebra, the limit as x goes off to infinity of 1 divided by x times x gives us 1, divided by, we're still going to have 1/2 in a denominator, and then x to the negative 1/2 times x gives us an x to the positive 1/2. I feel pretty strongly that I should have multiplied top and bottom by 2x, so I'm going to go back and multiply by 2x. I do that so that 2 can cancel out with that 2, and we get a 2 in our numerator without the 1/2 in our denominator. Sorry, the compound fraction was bugging me. Regardless, our answer will be the same. Now, as we let x increase without bound, the square root of x increases without bound. So this becomes 2 over something infinitely large. If the denominator grows without bound, this whole thing limits to 0, assuming the numerator also does not increase without bound. So, L'Hopital's rule. We're using derivatives to help us evaluate limits. We still might have to do some algebra to evaluate limits, but L'Hopital's rule is going to provide us the tools needed to allow us to use algebra later on. So moving on to example 4. Let's say we wanted to find the limit as x goes to 0 of the tangent of x minus x all over x cubed. And so the first step is to try and apply this limit. When we do, the tangent of 0 is 0, and the tangent of 0 is 0, so our numerator becomes 0 minus 0. So we get a 0 in our numerator, and we get a 0 in our denominator, which is fine. That means we're going to use L'Hopital's rule. We know that the limit as x approaches 0 of the tangent of x minus x all over x cubed is equal to, by L'Hopital's rule, the limit as x goes off to 0 of the derivative of tangent is a secant squared, and the derivative of x is 1 all over 3x squared. And now, as x goes to 0, well, the secant of 0 is 1, so the secant squared of 0 is 1. Our numerator becomes 1 minus 1, which is 0, divided by 3 times 0 squared is also 0. Fine. We can apply L'Hopital's rule again. So equal, by L'Hopital's rule, limit as x goes off to 0 of, so secant squared of x, this is a secant of x squared. So when we take the derivative, our power is going to come down. 2 times the inside, secant of x, 1 off the power to the 1, times the derivative of the inside, and the derivative of secant is secant tangent. Minus the derivative of 1 is 0, so minus 0, all over, we would get a 6x. So, going through, looking at this, when x goes to 0, we get 2 times 1 times 1 times 0 all over 0. We're still in an indeterminate form. I'm going to go through and I'm going to do a little bit of algebra right here to try and clean everything up. So, we're going to say that this 2 and that 6 are going to interact with each other, and I'm going to pull a 1/3 out. So for the sake of argument, I'm just going to say that this is equal to 1/3 of the limit as x goes off to 0 of, and I'm going to group these two secants, secant squared of x times the limit as x goes off to 0 of the tangent of x divided by x. Because remember, you can take the limit as x goes to some value of f of x times g of x, and you can break it up at multiplication. That's equal to the lim of f of x times the lim of g of x. And that's what we did here. We went from the limit of the secant squared of x times the tangent of x to the limit of secant squared of x times the limit of tangent of x. The reason why we did that is because we have no issue evaluating the secant squared of x. We know this thing is equal to 1/3 times the limit as x goes to 0 of secant squared of x is 1 times the limit as x goes to 0 of the tangent of x divided by x. Perfect. So don't be afraid to use your limit rules to break these things apart. If there is one part in particular that's giving you issue, focus your attentions on it. Evaluate what you can, turn them into constants, and just group them out front. Well, this is going to be, and when we go to try and evaluate this, this becomes 1/3 of 0 divided by 0. So we got to use L'Hopital's rule again. This is going to be equal to 1/3 of the limit as x goes off to 0. The derivative of tangent is a secant squared divided by the derivative of x is just 1. Now we can evaluate this limit. The limit as x goes to 0 of secant squared of x is equal to 1. 1 divided by 1 is 1. So the value of this limit is equal to 1/3. There are a lot of little things floating on around here I want to draw your attention to. The big one is, don't be afraid to recursively apply L'Hopital's rule. When do you stop is a natural question to ask. When you can evaluate the limit is, I think, the natural answer to give. There are more subtleties to that, but the object of this, the goal, I'll say, is not to get you to apply L'Hopital's rule an infinite number of times. The goal is to get you guys to apply L'Hopital's rule as many times as you need to get to a number. So there isn't a set, you always do it once, you always do it twice. Oh, on these homework problems, you're always going to do it 6 times. It's like using the product rule, or it's like using the chain rule. You use it as need, you use it as much as you need, and then you put the tool back in your toolbox when you're done with it. As soon as you can evaluate limits, stop doing L'Hopital's rule. This right here, this going from this step to this step, that was kind of tricky, I'll admit that. The 1/3 I don't think is going to give you guys any issue, but I can evaluate these secants. The secant squared as x goes to 0, that isn't a problem. So let's evaluate those first. And then we're really getting our issue from this tangent of x divided by x. This is where our 0 in the numerator is coming from, and this is where the 0 in the denominator is coming from. So we grouped those together so we could focus our attention on them. Once you can evaluate smaller parts of a limit, do it. There's no reason to keep this thing floating around until the end. What if you didn't notice it? You can apply L'Hopital's rule right here, because after all, you will get a 0 divided by 0, and it will get you back down here to 1/3. You don't have to make this clever sort of observation, but I will warn you, it's always good, especially when there's trig things floating around because of the way they interact, that if you wanted to apply L'Hopital's rule here without doing this algebra, you would have to deal with a secant squared of an x times a tangent of an x in your numerator, which is fine. You would do a product rule with a chain rule and you would be able to get out of it somehow. But the problem is made easier when you take a minute to look at the little parts that you have. Like I said, it's the white knuckle approach to calculus versus the big picture approach to calculus. When I was learning calculus, I did the white knuckle approach. I was comfortable applying these rules, and I wasn't bothered by the algebra per se. But it took me time, it took me years to get used to doing this more big picture approach to calculus. So definitely think of these equations as molecules, and you want to go in and you want to see what little elements make up the molecules. And if some elements play nicely, then go ahead and let them play nicely and focus your attention on the things that don't. So this next example is geared at showing you guys what happens when you accidentally apply L'Hopital's rule when you shouldn't. Let's talk about the limit. As x goes off to a pi from the left of the sine of x divided by 1 minus the cosine of x. So these are going to be peppered throughout your homework assignment to get you guys to break you out of that white knuckle approach. So let's answer this correctly first. So correctly, you always want to see what if I just let x be equal to pi. What happens? These things are continuous everywhere. The from the left doesn't necessarily matter that much in this problem. So let's figure out what's going on here. If we plug x is equal to pi in, well, the sine of pi is equal to 0, and the cosine of pi is equal to -1, so we get 0. Perfect. This is it for this problem. No tricks. We get 0 over 2, but that's equal to 0. I just skipped that step going from here to here. What if we made a mistake? What if we didn't notice that? What if we're still learning and the book presented us a tool to use? What if you applied the tool to this problem? Limit as x goes to pi. Well, let's say you didn't try and directly apply this limit in. What if you say, well, I've done L'Hopital's rule in the last 5 problems, let's do that here. Sine of x all over 1 minus cosine of x. Let's say that this is by L'Hopital's rule, and I feel very compelled to strike this out in a different color, indicating that we know this isn't true. Limit x goes to pi of derivative of sine is cosine of x divided by 1 minus the cosine of x goes to a sine of x. And now this is going to go off to the cosine of x, the cosine of pi is going to go off to 1, and our denominator is going to go to 0, so this goes off to a positive infinity. Perfect. So, let me think. From the left, we're actually going to make it to a negative infinity. I'm sorry. So, when we apply L'Hopital's rule, when we apply L'Hopital's rule, we have to make sure that we have an indeterminate form. That's the other half of that thought. L'Hopital's rule only applies when we have 0 divided by 0, or we have plus or minus infinity over infinity. And by plus or minus infinity, I mean that we can have plus infinity over plus infinity, we can have negative infinity over negative infinity, we can have positive infinity over negative infinity, or we can have negative infinity over positive infinity. These are the 4 things that get wrapped up into this plus or minus infinity thing. We didn't have that over here. Over here we had 0 divided by 2. So be careful. You can only apply L'Hopital's rule to things that look like this. So always try and evaluate limits like normal. Don't get used to just applying your new rule. So some problems aren't going to be set up for you. Let's talk about example 6. For example 6, we want to evaluate the limit as x goes off to 0 of x times the natural log of x. And if we immediately try to apply this rule, we get a 0 times a negative infinity. That's any sort of 0 times an infinity is another one of our indeterminate forms. We're going to talk about them more in a little bit. But what L'Hopital's rule says is we need to have something divided by something else. We have 2 things being multiplied together, but we can algebraically manipulate this thing. This thing is equal to, just by algebra, the limit as x goes off to 0 of the natural log of x, and multiplying by an x is the same thing as dividing by a 1 over an x. You can convince yourself of that. What happens if we multiply top and bottom by an x? We'll get right back to where we started. Perfect. And now, as we go to 0, let me double check something. Perfect. This problem needed a plus sign, and it still needs a plus sign. If we didn't have a plus sign, this limit wouldn't exist. So as we approach 0 from the right, this thing is going to tend to a negative infinity divided by an infinity. It's one of our L'Hopital forms. It's one of our indeterminate forms. So that means we can apply the limit here. And you're supposed to ignore what I have in green. We're going to apply this here. This is going to be by L'Hopital's rule, the limit, as x goes off to 0 from the right, the derivative of the natural log of x is 1 over x, divided by the derivative of what is x to the negative 1 is a negative x to a negative 2. So now we want to go through and we want to algebraically manipulate this thing to see if we can just plug that limit in. I'm going to rewrite this to hopefully make it more obvious. Limit x goes off to 0 from the right. 1 divided by x is x to the negative 1 divided by x to the negative 2, and this minus sign I'm going to stick out front. I can go through and I can multiply this equation top and bottom by an x squared to give us, too many pens in my hand, to give us the limit as x goes off to 0 from the right of a negative x squared times a negative x squared gives us a 1, x squared times x to the negative 1 gives us an x. And as x goes to 0 of negative x, this whole thing equals 0. So really, the big trick here, the thing that I'm trying to show you, is that we need, for L'Hopital's rule to work, we need an f of an x divided by a g of an x. And that wasn't immediately given to us. But by our algebra skills, or by properties of algebra, through algebraic techniques, that's a better way of saying that, by employing certain algebraic techniques, we were able to rewrite this equation from the product of two things to the quotient of two things. Once you have the quotient of two things, make sure that you have an indeterminate form, and then you can apply L'Hopital's rule. You're free to do any sorts of valid algebraic techniques in order to get an equation in this form. So little tricks like this can definitely come in handy. Also, little tricks like this really come in handy with trigonometric functions too. If you're getting a 0 times infinity or something like that, tangent immediately comes to mind, because tangent will go off to positive infinity or go down to negative infinity. Remember that multiplying by a cosine is the same as dividing by a secant. Multiplying by a sine is the same as dividing by a cosecant. So there's a lot of different ways you can algebraically manipulate multiplication and turn it into division. Just be aware that you need something of this form for now. You need something of this form or something of that form in order to apply L'Hopital's rule. So there were actually, looking here, there were two different ways we could rewrite this. And, you know, a lot of times teachers show you the correct way to do things, but I want to show you what happens if you make a not the best choice, is a good way of saying that. So still example 6, talking about limits. X going off to 0 from the right of a natural log of x times an x. There we go. Same problem as we had right here. But before, I put the x on bottom. Well, we could have done the same trick with the natural log of x. It's equally valid to say that this is equal to the limit as x goes off to 0 from the right of x divided by 1 over the natural log of x. So, and if we wanted to go and apply L'Hopital's rule, this is equal by L'Hopital's rule to the limit as x goes off to 0 from the right of 1 divided by, and the natural log of 1 over the natural log of x is the same as the natural log of x to the negative 1. So when we take this thing's derivative, we'll get a negative natural log of x to the negative 2, all times the derivative of the inside, which is 1 over x. We can move our x up into the numerator, that's fine, which is equal to, and I'm going to move that minus sign up, limit x goes off to 0 from the right of negative x all over the natural log of x to the negative 2. So we're getting something more complicated. We're gonna, gosh, what's a good way? So as we continue to take this thing's derivative, it's never going to settle down to something nice. We're always going to be getting all of these x's in the numerators and an increasing number of natural log of x's in the denominator. This thing kind of explodes. We'd still get a 0 over 0, so let's say, well, what if we try and do it again? Sometimes we have to apply L'Hopital's rule a couple times, so let's see what if. Negative 1 over negative 2 natural log of x negative 3 times 1 over x equals, by algebra, limit x goes off to 0, negative x over negative 2 ln of x negative 3. It's getting worse. Oh my goodness. L'Hopital's rule is supposed to make this thing easier, and it's making this thing worse. Well, remember, there were two different ways you could break up x ln of x. You could either make it x divided by 1 over the natural log of x, which led us down a path of pain, or we could have done x ln of x to equal ln of x divided by 1 over x, which led us to an answer. How long do you trek down the path of pain until you lose faith in it is a good answer. There isn't a point when it's immediately obvious to everybody that this is the path of pain that doesn't take you to an answer. My suspicions started right here when we got back to something that kind of looked like our original, and my suspicions were confirmed right here when once again we're back at something that looks worse, that's more difficult to deal with than our original. If the problem is getting harder by L'Hopital's rule, if you're generating a lot of things, see if there's another way you can break up the problem. L'Hopital's rule is supposed to make the problems easier, but as we've seen, sometimes they do generate a lot of extra stuff, so you got to be careful when you apply L'Hopital's rule, especially when you're doing these sorts of algebraic manipulations. Be careful. Don't assume there's only one way to approach these problems. I'll say that. Don't assume that there's only one way to approach the problems, because right here there's two different ways, and there's technically an infinitely many different ways we can go from here to something over here that's valid for L'Hopital's rule. After the first or the second application of L'Hopital's rule, your problems should be starting to condense a little bit. I wouldn't be surprised if you had to do it 3 times, maybe 4 times in one problem. But definitely when you start to apply L'Hopital's rule more than once, be careful with your derivatives, and make sure that you don't lose sight of your goal. Your goal isn't to just apply L'Hopital's rule, your goal is to get a number from a limit. So we have some other indeterminate forms. We call these indeterminate differences. And there are things like limits as x goes off to a of some f of x minus a g of x. And we get something like an infinity minus an infinity. The reason why it's an indeterminate difference is we don't know if one of these infinities is bigger than the other. If this infinity is bigger, then we would go to positive infinity. If this infinity was bigger, we'd go to negative infinity. It's possible that these infinities are relatively the same size and this difference goes to some finite number. We just don't know about infinity minus infinity. But what we can do is we can algebraically manipulate problems such as the limit as x goes off to 1 from the right of 1 over the natural log of x minus 1 over x minus 1. And if we try and if we just try and directly apply this limit, well, 1 over the natural log of x as x goes to 1 from the right, that's going to go to a positive infinity. We'll get this minus sign, and as x goes to 1 from the right, we'll actually get an infinity out of there. So, infinity minus an infinity. We want to be able to use L'Hopital's rule, but remember, for L'Hopital's rule, we need an f of an x divided by a g of an x. Well, we're taking the difference of two fractions here. In order to do that, we need a common denominator. So let's put these things on a common denominator. This is going to be equal to the limit, as x goes off to 1 from the right, of x minus 1 minus the natural log of x, all divided by the natural log of x times x minus 1. So if we try and directly apply the value of this limit, if we see what happens when we let x be equal to 1, we're going to get 1 minus 1, which is 0, minus the natural log of 1, which is also 0, divided by, so our numerator is 0, divided by 0 times 0. So we still have one of our now we have an indeterminate form. So we know by this thing is equal to, by L'Hopital's rule, the limit as x goes off to 1 from the right of the derivative of x is 1 minus the derivative of 1, which is 0, minus the derivative of natural log of x is 1 over x, divided by, now we've got a product of two things. We take the derivative of the first times the second plus the first times the derivative of the second, which is 1. So I'm going to go through and I'm just going to rewrite some stuff here. We're going to call this a limit as x goes off to 1 from the right of, we'll just say 1 over 1 minus x, divided by, this will give us a 1 minus 1 over x plus a natural log of x. And now what we want to do is we want to see if we can directly apply this limit. Well, as x goes to 1 from the right, 1 take away a positive infinity is going to give us a negative infinity. So we get a negative infinity all over 1 take away infinity plus 0, another negative infinity. So we still have an indeterminate form. So what we want to do is we want to reapply L'Hopital's rule. So, and I don't want to crowd myself too much, so let's say the limit as x goes off to 1 from the right of 1 over 1 minus x divided by 1 minus 1 over x plus the natural log of x. Perfect, so before we apply L'Hopital's rule, let's multiply top and bottom by an x. X over x. Just to make our algebra a little bit easier, or honestly to make our future calculus a little bit easier, this is going to be equal to the limit as x goes off to 1 from the right. X times 1 is an x minus x times 1 over x is 1 divided by x times 1 is x minus x times 1 over x is 1 plus x ln of x. And we still want to check, we'll get a 0 divided by 0, so we're still in an indeterminate form, 0 over 0, which makes sense. Over here, we will, this is equal to, by LH, by L'Hopital's rule, the limit, as x goes off to 1 from the right, derivative of x is 1, derivative of 1 is 0, divided by derivative of x is 1, derivative of 1 is 0, plus the derivative of our first times our second plus our first times the derivative of our second, a product rule in that denominator. So this is equal to a limit as x goes off to 1 from the right of 1 over, we have a 1 plus x divided by x is another 1, 2 plus the natural log of x. And now finally we can just directly plug this thing in. The natural log of 1 is 0, so this is equal to 1 over 2 plus 0, or 1/2. So this problem was kind of long. This problem was tricky. Let's talk about it. Indeterminate differences, well, these are going to be fractions. We know how to combine fractions. We put them on a common denominator and we combine them. Once we have something that looks like an f of x divided by a g of x, which we have right here, then we're set up to apply L'Hopital's rule, assuming that this limit gives us one of these indeterminate forms, which it did. We applied L'Hopital's rule, we tried to apply the limit, it didn't work, so we applied L'Hopital's rule again. Well, we did some algebra, and then we applied L'Hopital's rule again. Every step, you try and evaluate your limit. If you can, you're done. If you can't, see if you have an indeterminate form. If you have an indeterminate form, use L'Hopital's rule. If you don't have an indeterminate form, see if you can make one, and then apply L'Hopital's rule. L'Hopital's rule is a powerful tool, and it's worth the effort to try and construct something that you can use it on. After all, it's a fairly straightforward result once you get it in the form that you need. So don't be afraid of algebraic manipulation in this. Do what you need to do. Don't be afraid to multiply by x over x's and manipulate this thing. Don't be afraid if these problems take 5, 6, 7, 8 steps. They take me 5, 6, 7, or 8 steps. And I've taught this class a couple times, so don't worry if it's not immediately obvious what algebra you should use. These things take time, they take practice. You have to get used to what's going on. So, like I said, don't get discouraged. These definitely can take some time. So, example 8. Not all. Well, I'll write this. Example a limit x goes off to infinity of an e to the x minus an x, some parentheses, gives us an infinity minus an infinity. What do? We don't really have any fractions here. How can we deal with this problem? Well, this is kind of tricky. Equals limit x goes off to infinity. We can factor out an x. X times e to the x over x minus 1. Now, this is something that's actually a little bit easier to deal with. We can break limits up at multiplication, so going over here to give me some space, limit x goes off to infinity of x times limit x goes off to infinity of e to the x over x minus 1. The limit as x goes to infinity of x is going to be infinity, but this right here is going to give us an infinity divided by infinity minus 1. This right here is an indeterminate form. So that means this whole thing is equal to, it's equal to by LH, and it's equal to by LH. This first part, this isn't causing us an issue. It's also not a fraction. There's no point in applying L'Hopital's rule to it. We're not allowed to. Is equal to, and I'm just going to leave it floating around out front, limit x goes to infinity of x times limit, and for good measure I should put parentheses there, limit as x goes off to infinity of derivative of e to the x is e to the x all over derivative of x is 1 minus 0. Well, we can now directly apply this. This is going to be equal to an infinity times an infinity. And that's fine. Something that's infinitely large multiplied by something that's infinitely large has to be something that's infinitely large. As compared to, say up here, you don't know what something, because you don't know how much to take away. You have no idea, and not you as in you personally, but we as humans, we don't know which one of these quantities is larger, so it doesn't necessarily make sense to talk about taking one away from another. But if you've got something that's infinitely large and you increase it by something that's infinitely large, everything's going in the same direction. They're growing in the same direction. Just like if you have something that you can take negative infinity away from negative infinity, you can add infinity to positive infinity, but when your signs are opposite, you just don't know the relative sizes of those infinities, so you don't know which one is bigger, which one is smaller. So when you have an infinity minus an infinity, you have to algebraically manipulate it. We also have indeterminate powers. So let's say if we had something like the limit of f of x to the power of g of x. So anything that's of the type 0 to the 0 after we evaluate this limit, infinity to the 0, or 1 to the infinity are indeterminate powers. So our trick is that if we have y is equal to some f of x to the power of g of x. Well, we could take the natural log of both sides, and we get that the natural log of y is equal to g of x times the natural log of f of x. So, we're going to use some logarithmic differentiation and some L'Hopital's rule in order to deal with our indeterminate powers. So, example 9. Example 9 wants us to calculate I just crossed an L. Calculate the limit as x goes off to 0 from the right of, lost my spot, 1 plus the sine of 4x, all with an exponent of a cotangent of x. So we want to evaluate this limit. We want to calculate this limit. We want to get on to the next problem. How do we do that? By solving this problem. Limits, you always want to apply this value in here. 1 plus the sine of 0 as we go to 0 from the right is going to be 0, and cotangent diverges up to positive infinity. So this would give us a 1 to n infinity. We're going to be in one of our indeterminate forms. So what we want to do is we want to algebraically manipulate this thing and use L'Hopital's rule. Well, if we know that y is equal to 1 plus the sine of 4x to the cotangent of x, that means the natural log of y is equal to the cotangent of x times the natural log of 1 plus the sine of 4x. And now what we want to do is we want to take this, that means, the limit of, as x goes off to 0 from the right of the natural log of y is going to be equal to the limit as x goes off to 0 of the cotangent of x times the natural log of 1 plus the sine of 4x. And so what happens here? Well, here, if we let x go off to 0, from the right, well, cotangent is still going to go off to a positive infinity, and we'll get positive infinity times 0. Infinity times 0 is one of our indeterminate forms. So what we need to do is we need to apply L'Hopital's rule. Unfortunately, L'Hopital's rule only works for quotients of functions. So we need to algebraically manipulate this thing. Natural logs are kind of clunky to manipulate, but multiplying by a cotangent is the exact same thing as dividing by a tangent. Limit x goes off to 0 to the right of this thing, the natural log of 1 plus the sine of 4x divided by the tangent of x. Perfect. So what happens when we try and evaluate this thing? We get 0 divided by 0. The tangent of 0 is 0, so we get one of our indeterminate forms. So we can apply L'Hopital's rule. Equal to, by L'Hopital, limit x goes off to 0 from the right of, we're going to do 1 divided by 1 plus the sine of 4x times the derivative of the inside. Well, the derivative of 1 is 0. The derivative of sine of 4x will give us 4 times the cosine of 4x. All divided by the derivative of the bottom, and the derivative of tangent is secant squared. Perfect. So now we want to see if we can, well, let's just use some algebra at this point. Let's make everything look a little bit nicer. This is equal to a limit x goes off to 0 from the right of, I'm going to say 4 cosine of 4x divided by 1 plus the sine of 4x. That whole numerator is on top of a secant squared of an x. And if we want to directly apply, now we want to see if we can directly apply this thing. Well, the cosine of 0 is 1, so this numerator, the numerator of our numerator, goes to 4 divided by 1 plus the sine of 0 is 1, all divided by 1. We're like, sweet, this thing is equal to 4. But the thing is we know that the limit as x approaches 0 of the natural log of y is equal to 4. The limit as x goes off to 0 of the natural log of y is equal to 4. Well, what we want to do is we want to raise both sides of this equation to e. What it says, e to the natural log of y, well, I'm not going to try and cram that down there. We're here. Limit as x goes off to 0 from the right of the natural log of y is equal to 4. Like I said, take this whole thing and make it an exponent for e. What you do to one side, you do to the other. Now, we have a rule that says that e to the limit of f of x is equal to the limit of e to the f of x. And we're going to apply that here. This left-hand side becomes the limit as x goes off to 0 from the right of e to the natural log of y, and that's equal to e to the 4th. Well, e to the natural log of y is just y. So we get the limit as x goes off to 0 from the right of y is equal to e to the 4th, which is the answer we want. It might not look exactly like it, but remember what y is. This shows that the limit as x goes off to 0 from the right, y is 1 plus the sine of 4x to the cotangent of x is equal to e to the 4th. Read left to right, at least in this language we do, so I'll put those over there. Indeterminate forms, or indeterminate powers, I should say. The issue is with the power. So what tools do we have to gain access to powers? Well, logs, natural logs. They are our go-to tool in our toolbox to gain access to powers. So this is a lot of steps, a lot of the why it actually behaves that way. We take the natural log of both sides, we algebraically manipulate that hand side until we get a number. We have to remember what all this means, and then so we bring it back in terms of the problem, in terms of the question. You don't have to call this thing y. You really could. You could just go through. You need something on the left-hand side. You could either put a number sign and follow it through, you can put y and follow it through, but you do need to manipulate both sides of the equation for these kinds of problems when you're dealing with these indeterminate exponents. And that's just because you solve the right-hand side, and then you have to translate the right-hand side back into terms of the left-hand side. So, indeterminate powers, natural logs, L'Hopital's rule. Don't forget to answer in terms of the problem. So our final example for the day, example 10. We're going to calculate, we're going to evaluate, we're going to find the limit as x goes off to 0 from the right of x to the x. Perfect. Well, this would give us a 0 to the 0. It's one of our indeterminate powers, and we go, oh gosh, that means I need to do something. This one isn't just straightforward. Well, the issue is with the power. We can't have 0 to the 0. We can't have 0 to the infinity. We have issues with this exponent. So when we have issues with the exponent, that means we want to use logs. We know that, so with this problem, we have y being equal to x to the x. So that means the limit as x goes off to 0 from the right of y is equal to the limit as x goes off to 0 of x to the x from the right. We can take the natural log of both sides. That means the limit as x goes off to 0 from the right of the natural log of y is equal to the limit as x goes off to 0 from the left of x times the natural log of x, which we've seen before. We've seen that right here in example 6. In example 6, we showed that the limit as x goes to 0 from the right of x ln of x is equal to 0. So, without going through all this work again, I am going to say that this is equal to 0. And it's really good, and I'll put an asterisk over here because I should have left myself some space, by previous work. There is nothing wrong. In fact, it is better, it is good to use previous work. You've already done all the work to go from here to here. So by previous work, and you could say, see example 6, we know how to go from here to here. You've already showed that you know how to go from here to here, so go ahead and just use your results. Your time is valuable. You don't have to go through and do the same things twice, especially if you tell the reader, and once again, I'm your reader, where you're getting your results from. As long as your reader knows you didn't just shamelessly copy it off the internet or something like that, then yeah, go ahead. Go ahead and use by previous work. By previous work, we know this. So I'm just going to write, we know that the limit as x goes off to 0 from the right of the natural log of y is equal to 0. Well, if we take both of these sides and we make them an exponent on e, we get the limit as x goes off to 0 from the right of y is equal to e to the 0, which is 1. Well, what is y? Y is equal to x to the x. So we have shown that the limit as x goes off to 0 from the right of x to the x is equal to 1. So, two takeaways. One, use your previous work. You've already done all the work for it. Go ahead and just use it as you need. And two, in our issues with exponents, we're going to be using logs. I typically use a natural log for the sole fact that ln has one less letter than log. And when I write log, I have to put a base b. So there's just more stuff I have to write. I write ln, and you use natural logs to get at exponents. Once you're at the exponent, then you can use whatever tricks you want here. We use L'Hopital's rule. In this problem, we used previous work to get to here. Then this is really the new part where you get a value over here, but the natural log of this limit is equal to 0. So we don't want to know what the natural log of the limit is. We cared about the limit of this thing. So we raised both sides to a power of e. So that's largely it for just kind of practicing L'Hopital's rule. For your homework for this section, go off and do an 11 through 67 every other odd. Be careful about your indeterminate forms. L'Hopital's rule is going to come back next section. I don't believe this book gives it a formal theorem, but we're going to use it for horizontal asymptotes. Mainly we're going to be taking limits as x goes out to infinity, and let's say we had some polynomials. Let's say we had x squared plus 1 over x cubed plus 2. Well, this would go to infinity divided by infinity, and if we applied L'Hopital's rule 2 times, we would eventually turn this into a 2 divided by a 6x, which would go off to 0, because that denominator gets huge. Limit x goes off to positive infinity, let's say x to the 4th minus x cubed all over 3x squared minus 1. Well, now if you look, the degree of the denominator is smaller than the degree of the numerator. This will go off to positive infinity. And the limit as x goes off to 0, let's say 3x cubed all over 2x cubed minus 1, is going to go to 3 halves. These degrees are equal. We're going to formalize this idea into a theorem. But L'Hopital's rule is really going to help us dealing with horizontal asymptotes in the future. All this is true is if we go to negative infinity. The only thing that changes is this one. If we go to negative infinity over here, we have to go to negative infinity over there. So, like I said, practice your L'Hopital's rule. Get used to the idea of when to use it, when you can just use normal differentiation techniques, and go ahead and practice with these. Send me an email if you guys have any questions. Talk to you next time. Bye-bye.